fourth presentation is from Nozar Naing from Texas Instruments, and her presentation is modeling measurements of high bandwidth device. So Nozar joined Texas Instruments in 2010 as a product engineer and eventually became a senior validation lead, PSI PI. She has led numerous projects in this role, including high-profile projects for large customers. So, Nozar, please take it away.
Thank you, Ian. Hi, everyone. My name is Nozar Naing. I'm a bench validation engineer, work for TestConX Instrument. In this presentation, I will talk about how do we do the high bandwidth measurement of the devices in like simulation world, also in like actual device measurement performance using the network analyzer. In this agenda, you will see the pre-silicon simulation. This is the design data that we got from the designer. This is just the modeling simulation result of the device by itself, including the package capacitance and the package performance. The second point, I will talk about post-silicon measurement. This is where we use the test feature with the actual device coming back in, and then we use the network analyzer and then do the measurement. We also do the study of 2 traces layout simulation data. Whenever we're doing the layout, we do the simulation of the data, and then when the boat come back, we measure with the network analyzer, and then we do the comparison. I will talk about pre and post data correlation, and then followed by the summary slide. A little bit information about the setup in general. The device itself is the USB 2.0 MAX switches. That's the power measurement IC. Addition to this multiple input and output pair, our device also have like power FET switches and some other additional circuitry. How do we control the input and output pair? We have like an I2C command or SQD command we can send through using the T-bar or the Chi debugger, and then make sure that desired input and output are connected. For the purpose of presentation, I'm not going to talk about all this input and output pair. I picked one of the input pair and output pair, and I will do this, show the study of the result. As I mentioned, I will use the network analyzer to measure the device performance, and then for the simulation purposes, using the advanced design system software to extrapolate the data and then to compare the results and so on. So in this slide, you will see the design simulation data. This is the purely package layer design that I got it from the designer. In this simulation, you will see the instruction load is like -2 dB, and then our device spec performance is like 850 megahertz. So that's the design spec. Design is up to around 1 gigahertz at the -3 dB. This is the 2 traces you will see. This is the positive input and the positive positive output, and then negative input and then negative output. In this next slide, you will see the general, how do I do the boat layout simulation. First, we decided how do we do the routing and stuff like that. This is routing is done by 90 differential routing. Then after we finish the routing, I imported in the software and then do the traces simulation. Just to be sure that we all understand the way to simulate the traces. Let's say if you have an SMA connector to the board using, you will see the layout input traces. You will see the layout input traces for 2 pair, and then layout output traces for 1 pair. So this is like positive in, positive out, negative in, and negative out. So from this layout simulation, you are expecting to get the following file: layout in, positive, layout in, negative, layout output positive, and then layout output negative. So these are all just the layout traces simulation that we will use later in our design measurement. So in this slide, you will see I already got the design sim data from the designer. And then I already have like a layout traces simulation that I did that I plan to manufacture later. For this PowerPoint, I'm trying to figure it out. Okay, if my device performance gonna affect anything if I added the layout traces that I'm gonna use. So in this simulation, you will see I comparing against the design DUT scene and then adding at my layout traces. And then these are the measurements here. It's a 990 and a 1 gigahertz. We saw slightly different changes, but not that significant. This gives us the confidence that we're gonna manufacture this particular board to the fabrication. In this slide, you will also see I have like a different path to compare it. So you will see like positive path and then negative path comparison here. How do we do the de-embedding structure? So there's if you see there is like a couple of methods that we can use for this particular study. We're using the open and short calibration method. So first, we building the 3 PCB fixture with the DUT with the traces on, and then DUT, there's no DUT installation, that's we call it open circuit, and then we short it to the ground. So these are the 3 features that we built. After that, we using the network analyzer and then measure those 3 fixture. So we're gonna have the S parameter find for every single measurement. In order to effectively remove the series parasitic, you have to transfer the C parameter, S parameter to the C parameter, and then do the math calculation. That will effectively remove the series parasitic. After you remove the series parasitic, the next step is removing the parallel parasitic. These are all including the math function. So and then I transform it to the Y domain, and then I subtract the parallel parasitic. The final step is that I'm converting back to S parameter and then do the study again. So this is the measurement performance of my open traces that I have in the board. So these are in the dB scale, and then these are the frequency. I simulate, I measured up to 5 gigahertz, and then this is the clear open with the trace length that you can see here. This is the measurement of the short trace. This is the short study, and then with the length that you're seeing here. So this is the measure. This is the one we got back the device and then do the measurement. This measurement includes the performance of the DUT plus text feature. You will see our device performance got down to 820 and then 840 megahertz from the different positive and negative pair. That means there is something in that feature affecting the device performance. And then we're going to do the proper de-embedding method in following slides. So I'm going to revisit here. So we're going to do S parameter converted to the C, and then to remove the series parasitic. And then this is the abbreviation that you will see in the following slides in the formula. This as such means the short measurement that I measured it from using the network analyzer. COP is the open measurement. And then this is the DU is the DUT plus the Fisher measurement using the network analyzer. After that, I will do the subtraction using in the Z domain, subtract out the series parasitic. So in this step, you will see everything was exported to the ADS software, and then I simulated from 300 gigahertz. This is 300 gigahertz kilohertz to the gigahertz. This is just for generating the signal. And then I put in the measurement data in here and then change the Z domain. This is the formula that I use in order to do the subtraction of the series parasitic. After that, ADUS will spit out the format that we require. This is another step that I was subtracting it. From the open measurement, I'm subtracting the series parasitic. The next step that we are doing, we have to remove the parallel parasitic by subtracting from the Y domain. So in the following slide, you will see the formula and then how do we do that. In this portion of the schematic, I'm changing from the Z parameter back to the Y parameter on all this interested parameter. And then in the following slide, this equation I used in order to do that parallel parasitic extraction. These are the formula that we are using, and then these are the equations that I'm going to write in order to split out the Y parameter of interest. And then in this slide, we are changing back to our S parameter domain. This is where you will see everything is de-embedded. Doesn't mean like all this parasitic that we're gonna see by device fixture that we are using are extracted out from that measurement. So you will see that device performance got significantly improved from the around 830 megahertz to the 910, 920. At this stage, we are seeing that, okay, my device performance is past the spec, but it wasn't what design telling us. It's supposed to be around 1 gigahertz, and then we are seeing around 70 megahertz loss in the design that we couldn't account for. From that, we are doing some study for measuring 2 trace just to make sure that our stack up information of the layout traces simulation versus the actual measurement without including any device performance and so on. So this is where I'm also going to show you what are the unaccounted loss that we're going to see. So in this RP and TP part, we are seeing 40 megahertz losses, and then RN and TN part, we are seeing 80 megahertz loss. So these are the ones that we couldn't account for, like I mentioned. And then you can clearly see in here, in like comparison between the design simulation 6 and 5, which is around 950 megahertz, and then 3 and 1 is my measurement data after I de-embedded. This is for another pair of the trace. It's about 990 and then 910 at the negative 3 dB measurement. So this is the slide that I'm showing you that we are doing study for the 2 millimeter traces. It's just the open traces that we also added in our boat, the same boat that we are using measurement for the text feature. It's just like an import to like you just connect it to network analyzer, and then you can just measure this particular traces, and then we do comparison against the measurement data versus the simulation data. In this simulation, that you will see this is the measurement data, sim data versus the NA measurement data. So these are the 2 traces that I use. And then you will see the M1 and M2. The difference between that 2 traces between simulation and the measurement data is 0.02 dB, which is pretty negligent if the frequency of interest that we are looking for. We are looking for frequency of interest around 850 megahertz. So that assures that our layout simulation is good, stack up informations are correct. That kind of align with our actual device measurement. And then I also do measure it up to 5 gigahertz just to see what is the performance of the traces at 5 gigahertz. You will see around 4 gigahertz, we have a loss of 0.2 dB at the higher frequency. But like I mentioned, the interest point is 850 megahertz, which is pretty less impact of the traces that we're gonna see. So in this PowerPoint, I will show you how we compare again. So here's the layout traces that we use, and then design sim data that we do. This is a pre-silicon simulation, and the layout traces that we are using. This is the board that coming back after the manufacturer. So we're gonna see the comparison between that two measurements. So in this slide, you will see there's like the TP and the TP and the RP measurement. Marker that I put in here is marker 9 and marker 7, around 990 and then 850 megahertz difference. So that means that we are seeing some of the losses that it wasn't accounted for. It could be either measuring the network analyzer and then some of the variation of the fabrication that we couldn't account for. That's why you are seeing some of the losses in here. So the red line is the pre-silicon data, and then the blue line is the network analyzer measurement, including the DUT performance plus the fixture. According to our simulation, we shouldn't see any of these losses, but there is certain things that we cannot control it for, of course. This is for the negative pair of the input and output. This is where we see like measurement data is around 830, and then there's simulation data with the traces is pretty aligned with the design simulation, which is the 1 gigahertz. So we stay seeing around 170 megahertz that we couldn't account it for. In this PowerPoint, I will show you the summary of the data. After taking care of losses due to the traces, we are still seeing 70 megahertz loss, which are unaccounted for. Then we had a couple of meetings with the designer just to investigate the sensitivity of the device itself. The 70 megahertz correspond to 350 femtofarad of extra cap on each side of input and output. So our device itself is pretty sensitive. You will see this amount of capacitance can lose 70 megahertz. So this is what we are stop our investigation because we are doing all the studying according to here. So let me recap it. For the design sim data, we are seeing around 990 megahertz, and then we measured it with the network analyzer with the text feature device come back at the 850 megahertz. And then we also do the pre-silicon sim data where we have like a sim data plus text feature. It is coming back at the 990 megahertz, which is pretty good before we do the before we manufacture the board. After that, we manufacture it, and then everything is de-embedded in this particular step. We doing the series parasitic and then parallel parasitic extraction, and then the final measurement is the 920 megahertz. So with all the proper extraction, we still couldn't account for the 7 megahertz that was lost. We stopped this experience because our devices are very well above our specification of 850 megahertz, so we didn't do any further studying after this. These are just a summary of the pre-silicon that we are doing. So you will see that 970, 980, and then 840 megahertz. These are all supposed to be match to each other, but due to the fabrication process and encounter uncertainty, we are seeing some difference already in here. So these are the references that I use to calculate all this equation that I'm using, and so on. Is there any question, Yun?
Thank you, Nozar, for the presentations. Please put in your questions into the Q&A box if you have any questions. Let me start with the first question here, Nozar. That the first question will be what is the typical characterization for this kind of debt looks like?
So particular, because this is like very complex the data max switches. So we have a bunch of input and output pairs. So we couldn't really automate it like fully clearly. So we are using the network analyzer, power up the devices, and then individually hooking up the corset cable and then do the characterization for this particular block of the switch. We also have like some different block of the device that we do different characterization as well.
All right, and the other question is, was the RF layout done manually, or if it is not, then what tools did you use? And if there's any RF layout automation tools that can be used or was used in your study?
RF layout is used. We using the RTM software. We using that, but in order to simulate it, I just exported that layout into the ADS, and I do the simulation doing the ADS software. So it's like two steps that was required. The layout is done in different software, and then I just simulated using another software.
I see. Okay. The next question is, how many inputs and output pair does your device have? And how about other input and output pair measurements? Are they all show extra unaccounted capacitance?
So there's a high frequency pair. We have like 3 input pair and then 2 output pair. That's around like 1 gigahertz range. Yes, they all show the same extra capacitance that we couldn't account it for. The low pairs are around 240 megahertz. They are pretty much okay. Yeah, so the high frequency pair, we all see that particular unaccounted parasitic.
Thank you, Nozar.
And lastly, I would like to thank our sponsors who made this event possible, including free registration. Our premier sponsor is Kohu. Our emeritus sponsor is JonsTech. Our honored sponsors are ISC, IWIN, and TSE. Our distinguished sponsors are Backer Hot Watt, Innovative Circuits Engineering, JMT, Nidec SVTCL, R&D Altanova, UI Green. Our exhibitor sponsors are ELELS, MJC, Phoenix Test Arrays, and Smith's Interconnect. So please, when you talk to them, thank them very much for making TestConX 2021 possible. And an extra special thank you to our premier sponsor, Kohu, the market leader in test interface solutions for the most challenging applications. And thank you to ISC, the global #1 total test solution provider. With that, I will thank you all for attending and wish you a very good rest of your day, and look forward to seeing you again tomorrow at 7 a.m. Pacific time. So thank you.